Good morning, all. I think we are now refreshing after the breakfast, and we had to have three very important lectures in the area of nuclear power plant design, uh, and as Mr. Agarwal said, the three topics of nuclear fuel cycle, then nuclear power expansion, and SMRs. Now I will introduce the first speaker, that is Shri Bhardwaj, who will be speaking on nuclear fuel cycle. Shri Bhardwaj, he was the former chairman of Atomic Energy Regulatory Board and is a mechanical engineer from Delhi University with MTech from IIT Delhi. He has also served before being in ARB as the Director Technical and also CMD in charge of Nuclear Power Corporation of India Limited. And he is also in the board of NPCL. Apart from that, he also was chairman of Nuclear Fuel Complex Board, Hyderabad. Mr. Bhardwaj has been associated with number of areas, like with respect to the nuclear reactor design, and is a very important figure in our nuclear power industry within the department and outside. He has been associated with the design of the PSWRs, and he is an expert in the area of fuel, which he is going to talk about, and also on safety and design. So, with this vast experience, he will be a very big contributor and an influence on all of us. So with this, I'll request Shri Bhardwaj to start his talk. Thank you.
Thank you, Dr. Datta. You have gone beyond what was written here. So I will also go beyond what I have put in my slides, and I may take more time then. Well, the topic assigned to me by INS is nuclear fuel cycle. And whatever we have been listening since yesterday morning and today till evening is all revolving around nuclear fuel. When somebody said there is a safeguard, when there is somebody said there is energy, nuclear suppliers group, there are a lot of restrictions. Somebody said there is a defense in depth. You should have very high quality equipment. There is emergency preparedness, all because of nuclear fuel. All because of nuclear fuel. So this is the center point of whatever we have been listening since yesterday until evening. And you are aware of this. So I'm not going to talk anything new to you. You are all aware of this. I'm going to repeat in a very simplified manner so that we can put this topic within the allotted time. Next one, please. So what is nuclear fuel? Nuclear fuel which nature has given us is uranium. This is the only fuel nature has given. I think I will handle this. Then I can have this. Yeah, that will be better. This is the fuel which nature has given us, and in nature has further given us two isotopes of this fuel. Uranium-235, 0.7% only in the total uranium available, and uranium-238, 99.3%. Very often, and today morning, Shyam Sundar was talking to me on thorium. The perception is thorium is a fuel. So there is thorium, and it is talk of the town these days. But then, these two are not fuels. They are not fuels at all. What nature has given is only 0.7% of the uranium available in nature can be used as fuel. But it has also given a gift that if you use this uranium-235 intelligently, and uranium-238 anyway comes along with it, you cannot separate them out very much. So if it comes along, uranium-235, while it gives you energy, it also simultaneously converts a small fraction of uranium-238 into a man-made nuclear fuel, plutonium. Similarly, thorium can also be supported by uranium or plutonium. It depends again on how you adjust that in the physics. And you can produce from thorium-232, which is not a fuel, uranium-233. So both uranium-238 and thorium-232 are called fertile materials. They are fertile. If you put a proper seed into that, yes, you can get fuels. In today's lecture, I am not going to talk of thorium at all. This is a material for use day after, not even tomorrow. We have to wait for use of thorium. And the current reactors which are operating and which again the industry now will be interested in are using either natural uranium, as in pressurized heavy water reactors in India, and enriched uranium as used in pressurized water reactors and boiling water reactors. So there are two types of uranium, is natural uranium, and we slightly enrich that 0.7%, we slightly enrich to use it in other reactors which do not use heavy water, they use ordinary water. And this is nuclear fuel cycle as predominantly used in the world around. And what Government of India in the Shanti Bill has done, that they have opened some part of it to the private industry, to the private entrepreneurs. What they have not opened is, or rather what they have opened very liberally are these areas. That you can manufacture fuel. You can make fuel assemblies, and therefore it will require conversion to uranium dioxide in that same industry. You can make reactors and use that fuel assemblies, and you will have to store this fuel for a time which government has not specified in the Shanti Bill. How long? So these are the sectors which are open. There's a mention that yes, conversion to enrichment is also open, but we'll have to wait and see how that can happen, because that technology is very safe, kept safe by internationally. So this is I'm going to mostly concentrate on these three areas which are today open, but for the sake of completion, I'll be covering other areas, that is mining and what happens beyond discharge stored fuel, which you are likely to store. Uranium mining, this is a picture from Indian mines, Jadugoda, for example. This is the other mine close to Jadugoda where a truck is coming out deep in the earth, around 500, 600 meters down. We go, break the rocks, and the rocks are like this. And in these rocks in India contain 0.04% of uranium. So you crush these rocks, dissolve in acid, and separate out a concentrate, which we call as yellow cake, ammonium diuranate. It can be U3O8 concentrate. Today we are also doing some peroxides. In some concentrated form, the uranium is delivered to fuel manufacturers. Well, at this stage, I must tell you that though we have 0.04%, many mines in the world are also of the same grade, but they are not deep into the earth. They are quite open cast mining, like coal is being done in Australia and other places. So it's slightly convenient. Or there are very, Canada has mines which have not 0.04%, they have 10% to 20% type of uranium available in those mines. But we have in India like this, but many mines in the world are of the same grade if you go to Africa and all that. Now we said enrichment. The uranium concentrate which comes from after mining and milling, which is done at the site, for purpose of enrichment, uranium is converted to a gaseous form, uranium hexafluoride, which is a gas. And you put this gas in a cylinder and rotate that cylinder at a very high speed. What we are trying to do is use the centrifugal force on uranium-238 and 235, which are very close in mass, very, very close in mass. But still, if you rotate this at a very high speed, what you will get towards the center is more of uranium-235, and what you will get at the periphery is more of uranium-238. So if you withdraw from the center the stream of gas, it will have slightly enriched uranium, and keep on doing it in stages, and you can make enriched uranium. And this is how it is being made now world over. So you get enriched uranium, you get that concentrate, and it comes to a fuel manufacturer, where he makes the fuel assemblies. And he converts either the enriched uranium or the natural uranium into this sort of powder, which is uranium oxide powder, which is pure. All the impurities have been removed, and impurities are not allowed to enter into the reactor. It is a process similar to making medicines, so that impurities are minimized. Now this powder is pressed into cylindrical small cylinders. Nominally the dimensions may be 1 centimeter long, 1 centimeter in diameter. It could be plus minus few millimeters. So you press it and then sinter it. Sinter means just like the process of making bricks from the mud. You heat it at a temperature and you densify the whole thing. And similarly, these are heated at around temperature of 1600 degrees Celsius in the presence of hydrogen, so that all extra oxygen is withdrawn. And you make uranium oxide pellets. We call them pellets, sintered uranium oxide pellets. They are very strong. They are very high density. The density is around more than 10 grams per cc. 10.5 is what we use in PHWRs. The light water reactors will have slightly less density than this. They are so strong. They are actually stronger than, or in terms of density, stronger than steel. So whatever is happening in the reactors is happening inside this pellet. We'll come to it. Now these pellets are inserted into a tube, which is made of zirconium alloy. Zirconium is an element which refuses to absorb neutrons almost. It is like glass, light passing through glass. Neutrons pass through zirconium. And we want to play with neutrons in a reactor. Therefore, we are very cautious of using the material. So world over, in water reactors, the cladding, as we call it, on the pellets is made of zirconium alloy. And India makes these alloys in plenty. We have a lot of zirconium available in the country. We make these alloys, which are alloy of tin, iron, and with zirconium. Then the tubes are closed at the end by welding plugs. And the gas inside is inert gas. We are using helium. And all of the world people are using helium inside for filling. Helium is very good conductor of heat. Ultimately, we are interested in heat to be delivered to the coolant. For a PWR, pressurized water reactor, the fuel assembly could be as long as about 4 meters. You are seeing that the fuel pellets are pressed on one side by using a spring. Because when this fuel will work in the reactors, it will create many fission products. And some of the fission products are also gases. Though they are entrapped in that solid pellet, but over the time with small diffusion, the gases may come out. So this spring space is actually for that gases to get accumulated. So 4 meter long, in which maybe 3.7, 3.6 meter long pellets. And close at the ends, this is a figure of a manufactured fuel elements and closed at the ends. If you look at the fuel assemblies, on the right hand side you see PHWR fuel assembly, which we make in India in plenty. It is a simple assembly. You arrange all these number of fuel elements in circles around the central pin and weld at the end a plate and the other end a plate. The length of a PHWR bundle is only 50 centimeters, half a meter. Whereas the length of a PWR, we said, is 4 meters. Now in this 4 meters, there are a number of locations you find these spacers. At the top corner, I have shown one of the spacers. This is a very complex structure. And this comes out of design, yes, material choice, a lot of experience with this. Because this fuel assembly is going to remain in high velocity coolant for many years, and therefore the elements will vibrate. And to arrest that vibration, we use these spacers. These spacers in PHWR bundles are quite simple that way, because the length itself is very small. But PWR assemblies have these spacers. Manufacturing up to the element level, that is putting the pellet in a tube and welding at the ends, is easy. Anybody can do, and we are doing it for BWR fuel. But these spacers are very specially designed, and they need a lot of R&D to prove that the fuel elements will remain in position during reactor use. Now in this fuel, PWR fuel, you also see at the, on the side I've shown some rods. The fuel rods, plenty of them are fuel rods. A typical PWR fuel assembly will have 17 into 17 or 14 into 14 number of rods in one bundle. And most of them will be fuel rods. But there could be some guide tubes. In fact, at the bottom you see there is a VVR type of fuel. The guide tubes are projecting out. Here, in fact, you may not be able to spot, there are some black locations where these guide tubes are there. These guide tubes are used for inserting control rods, for controlling the power of the reactor or for shutting down the reactor. So these locations are being used for control rods, guide tubes. There are some empty tubes used as instrument tubes for measuring the neutron flux during operation. So the bundle may have at the center one instrument tube. All bundles may not be alike. Some bundles may have control rods, some may not have control rods. So there is a variety of, at least the type of fuel bundles with respect to enrichment as well as location of such tubes in a PWR. But in PHWRs, all bundles are alike. The control rods are not part of this. PHWR, heavy water, permits you to use control rods at a different location in the reactor. So all those bundles are alike. And the PWR assembly is about 4 meters long, as we already said. That 17 into 17 number of rods are fitted into 20 centimeter square section, and the weight is around 500 kilograms. For typical PWR bundle. The VVR bundle, which I'm going to show next, is slightly bigger than this. It may have weight of 600 to 700 kg. And instead of 20 centimeters square, it has flat to flat distance of around 25 centimeters, slightly less than. And as I already said, the assembly has vacant rod positions for inserting control rods. Some locations are used for neutron source or some other instrumentation. This is a similar VVR bundle which we are using in Kudam. Their performance is excellent. And you see the pallet dimensions are given. 7.5 millimeters, slightly less than 1 centimeter. Length is around 1 centimeter. Number of pallets will be loaded into this. This is boiling water reactor fuel as we use in Tarapur 1 and 2. This is, in Tarapur we use 6 into 6 assemblies. This does not have control rods within the bundle. Control rods are actually between the 4 bundles. It is a cruciform shape. As you know, this shape has been shown. Similar shape exists between the bundles. So control rods are not part of the boiling water reactor fuel. This fuel is manufactured in India for Tarapur 1 and 2. And these are PHWR fuels manufactured in plenty in India, nuclear fuel complex for 220 megawatts, and that is for 540 and 700 megawatt bundle. Now comes the use in the reactor again, which has been now opened up for privatization. Use in the reactor and storage is the responsibility of the private operators. Fuel manufacturing also is now available for private manufacturers. As we said, we can use only that 0.7% of uranium, but it also produces 99.3%. In proportion to 0.7% can be converted to plutonium. In fact, the plutonium generation starts right in the beginning. As soon as we start the reactor, plutonium gets started. And plutonium is a fuel, so it also starts participating in the heat generation. But at the end, you get some residual plutonium. This is what happens. The uranium atom, it receives one, we call it slow neutron, but that slow neutron moves at a speed of 2.2 kilometers per second. Enters into uranium, and the uranium atom becomes unstable. Uranium-235 atom becomes unstable. So will be plutonium-239 when it is produced. So it becomes unstable and breaks into two. With a very high kinetic energy, the broken parts try to fly away. But they are in a very solid pellet, very high density pellet. So there is no space for them to fly away. all that kinetic energy gets converted to heat, and plenty of heat, 200 MeV, which is 50 million times more than one carbon atom burning to produce carbon dioxide and heat. 50 million times. And that is where in nuclear reactors you use very less fuel compared to what you use in the coal. We'll come to that number. Now, two products have been formed. And in each reaction, the product could be different. Where you can break the atom, uranium-235 atom, the location where it will be broken will be different from reaction to reaction. So number of type of these products will be created. Number of types we'll come to. And they will deliver this energy. But they also deliver 3 neutrons, which are very fast neutrons. We'll have to slow them down. So we started with 1 neutron, and we got 3 neutrons. And that is the other wonder which we have. So 2 major light atomic nuclear. Lighter means lighter than U-235. They is broken into 2 parts. It gives plenty of energy, 50 million times than a carbon atom will give while in a chemical reaction. And 2 to 3 free neutrons. 2 to 3 means sometime 2, sometime 3. The average number could be from 2.2 for uranium-235. And the fission products are distributed like this. We said it can break at any location. So then if you look at number of fissions happening, there are over 200 different types of radioactive nucleides which are generated in the fuel, in that pellet. They are all bound in that pellet. And they are radioactive. What is the meaning of radioactive? Radioactive means that they are unnatural. They are not natural, and they will try to become natural, stable atoms. And in that process, they will release some radiations, alpha, beta, gamma. I'll not get into what is alpha, beta, gamma. I think they are well known. So they are radioactive. It could be, and mostly it is, that the next product they come to is again radioactive. So it continues as a chain for a long time. And all these products have, as yesterday Grover also said, is a natural process. So you cannot now control it. They have their own time of decay. They take their own time to decay to come to a stable stage. And this is where the safety starts. In that fuel pellet, which has only 0.7% or at the most 5% fissile atoms, which are likely to fission, that 0.7% getting converted to radioactive elements is the safety issue now. And why it is a safety issue? It will create large number of fission products, and they are, we said, releasing alpha, beta, gamma rays. Alpha and beta are particles or rays which cannot travel much distance. Though they have a lot of energy, but they cannot travel much distance because they are heavy. So they get actually mostly consumed within the pellet. They get stopped in the pellet, and all the energy is delivered within the pellet. And we said they have long life. So this energy is going to be delivered to the pellet for a long, long time. So the pellet remains hot. As well as it remains hot for a number of years. I have not put how many years. Just like plutonium is created by absorbing neutrons, some other elements are also created by absorbing neutrons, and we call them minor actinides. They are actinides. So they are also created, and they have very, very long life. This blue line, very long life. People say lakhs of years. Yes, they are. And they are also generating heat. So there are 2 types of issues. One is it is radioactive, and all these are radioactive. So for lakhs of years. And out of those, there are fission products which have shorter life, but they are also radioactive, and they are giving a lot of heat. So we have to handle now 2 things: radioactivity, radiations coming out for a long time from that pellet, as well as heat, and it is going to be almost perpetual. So this is a safety issue. So first is the radiation. Now this radiation is being generated inside this reactor, pressure vessel. And though when you manufacture the fuel, you are manufacturing manually. You can touch the bundle. You can actually the whole operation is done manually. You can handle the bundle in your hands. The radioactivity is so mild. But once it is seen the reactor, you cannot look at that bundle now closely. It has to be seen through shielding. Shielding means It should absorb all the radiations which are coming out from the fuel, and gamma radiations, which are just like X-rays, come in plenty and very high energy. So this now has to be shielded at all times. And that is where yesterday, time and again people said inaccessible area. This is inaccessible now. Once you have started the reactor, whole of this area is inaccessible to you. You cannot enter inside. And therefore the quality requirement, that the quality should be such that it survives the whole life. And the regulator will not agree. So it will ask you to inspect that. You cannot inspect because high radiation. So all has to be done remotely in an automated manner. And if you have some trouble, some weld to be inspected, which is very different, you will have to create toolings. So in this area, unless the quality is very high, you are going to spend a lot of additional time if any maintenance is required. So that is where time and again people said quality. And wherever you keep the fuel now, you will have to have shielding. This is thick shielding. This is about 1 meter thick concrete, heavy density concrete, to shield these fuel bundles. So now fuel has to be always shielded during its use and after its use. So that is the importance of shielding. Again, time and again we said radiation should not come to the workers, the occupational workers, radiation should not go to the public. You have to have shielding for the people itself. People can access all these areas. Outside areas they can access, but not inside. These are inaccessible. And to see that people can access, you have very thick shielding all around here. And this again, concrete has to be very high quality. Second is heat. Moment you shut down the reactor, the physics people say 7% heat is still there. But within the time in which the inertia of the water which is flowing and the extra capacity it has to absorb, for engineering purposes it is around 2% heat. 2% of the heat which is being generated in the reactor will have to be now handled. And 2% heat for 1,000 megawatt PWR means, looking at the efficiency of electrical generation, about 60 megawatts. 60 megawatts of heat has to be handled now. The reactor is shut down. So as far as the electricity generation is concerned, the reactor is shut down. But as far as the operator is concerned, it is not shut down. The reactor never shuts down for the operator. And that is very critical. Otherwise, you will have all those incidents. So decay heat from the discharge fuel, but since we said all the fission products, they keep on decaying with time, it also reduces with time. But how many years? For years together. So as far as you will have to, the storage of fuel is in the command of private industry now, you have to always pay attention to this cooling. And if you recall Fukushima incident, in one of the reactors which was shut down, the fuel was actually in the pool, but the whole world was worried that this fuel has got damaged, the cooling has been lost, and radioactivity is coming out. So you cannot now take a rest. Once the fuel has been irradiated, you have to shield it, you have to cool it perpetually. Of course, the amount of cooling required goes on reducing with time. So most important aspect of safety, which yesterday we heard in all lectures, is that heat produced should be equal to heat removed at all times. Whatever, if you are producing 100% power, the flow of the coolant should be that it matches with the 100% power. When you shut down, yes, 2%. After some time, you can reduce the coolant. But it has to be always matched with whatever heat is the generation, including even when the plant is not operating. As far as the operator is concerned, it is always under operation because it is generating heat. So once put in operation, the fuel is always hot and needs cooling almost forever, but at a decreasing rate. If you do not cool it, what happens? And what has happened elsewhere? This is what happened in 3 Mile Island. The operator was actually, the regulator recognized, and later on it was recognized, but not very openly stated, that the operator was not well trained. He focused fully on that the plant is operating and whatever signals he is getting are spurious signals. And he missed that yet actually the fuel is not getting cooled. It is not getting coolant. It's a lack of training that you are in a safety case now. And the fuel melted. In a matter of half an hour or few hours, the fuel melted here. So if you don't cool, this happened. It happened in 3 Mile Island. After 24 hours, they got time up to 24 hours to do something to cool that fuel. It was cooled for about 2 hours because the tsunami took time to reach that place. But once tsunami reached there, what they lost is all power supplies. And power supplies are feeding those pumps, which was cooling it, though up to 2% power only. Their batteries were lost. They had some passive systems which could be operated, but they were battery operated. And batteries were lost. So all powers were lost, and they also, Fukushima is right now in the memory. When it comes to Chernobyl, it was not the cooling. You know, nuclear fuel does not have something like calorific value. You have in coal. It cannot exceed, whatever you do, it cannot exceed that calorific value. But here, if you pump in more neutrons, more power. More power, if you can pump in more, so there is no limit. And if you can do it very fast, yesterday Grover said 10 to the minus 14 seconds, if you can, within that time frame, if your neutrons increases, and that is what happened in Chernobyl. In that time frame, the neutrons increased, and they had an area which is forbidden for the operator, not to operate the reactor at around 20% power. They were forbidden for the operator, but they didn't have an automatic control system to do that. And the operator somehow reached that area. And he continued to operate merrily, and he led it to that power. So, Chernobyl is an overpower incident, whereas other two are lack of cooling. There is another incident in a Hungarian plant, which is VVR, 440 megawatt. The reactor was shut down, and the fuel was needed some cleaning because some crud has deposited on the fuel. So they had some setup made outside the reactor during shutdown period to clean that fuel by a chemical process and simultaneously cool it also. They were doing it in the day shifts. At the night, they were to remove the fuel, keep it again in the pool and put it back. At the night, when the closing time came, that main operator who were familiar with the fuel, he said, why not? Now is a crane operator's job. Now he had to take it out and put it there. So all these people left. And the crane operator was not knowing it. His crane malfunctioned. So he said, okay, let me leave it like this. Tomorrow morning I will do the job. And in the night, the fuel melted. A shutdown reactor, after a few days, after 15, 20 days, the fuel melted. So it has to be cooled at all times, whether you are inside the reactor or outside. It has to be shielded at all times. And that is the safety about. All that you listened yesterday and today again you will be listening till evening is because of this fuel. And when fuel melts, what happens? We said there are some gases or some elements like cesium which become volatile at temperatures. So all these volatile and gaseous things will come out of the fuel. Solids will remain there. It may damage your floor and what is happening now in Fukushima. But these gases will come out in the public, in the containment. And if your containment leaks, they will come into the public. You will see that most of them have a short life. Half-life is 8 days, a few hours, minutes, hours. This is some years, but Krypton 85 is a noble gas, so it does not react. It will dilute on its own. But you look at this cesium, 137, 30 years of life. So if it comes out, and it has come out in Fukushima and in Chernobyl, and it is staying put for years and years together. It is half-life, so you have to see how many half-lives. So that is the emergency planning about. And today's regulations say, it will be covered in the evening, that under no circumstances people should be displaced from their locations permanently. You can have something as we had in COVID, few days of, okay, stay in your house. Few days you should take food only which is supplied to you. Few days, but not for 30 years into 6. So today's regulations do not permit this. So this cannot happen. Again, another issue which happens if the fuel is getting overheated is that zirconium cladding, or that for that metal, any metal reacts with oxygen in corrosion and produces hydrogen. But here in this case, at a certain temperature beyond 600 degrees Celsius, this reaction is very fast. When the fuel overheats because of lack of cooling, the interaction with water and its vapor provides oxygen to the corrosion reaction. Corrosion reaction becomes very fast, it is accelerated, and a lot of hydrogen is produced. It is not that only hydrogen is produced, this reaction is exothermic, it adds to heat also. And that is what happened in Fukushima and happened in 3 Mile Island. Both places hydrogen got generated. Fortunately, in 3 Mile Island, the hydrogen remained within the reactor vessel. The whole vessel and the system was intact. It did not come out. But the concern in 3 Mile Island was that this hydrogen can now explode anytime. Hydrogen with some amount of oxygen present can explode, can detonate. So that was a concern, but later on, as the hydrogen has been understood well, if it is in a closed space where, the oxygen generated is proportional to hydrogen, it cannot actually burst. But that was the concern at that time, and it remained all over the world that tomorrow the reactor will explode. It did not. But in Fukushima, it happened. What you saw on your screens after 24 hours is this hydrogen causing that explosion. And therefore, again, cooling of fuel at all times. And you can never, so all systems required for cooling of the fuel, it is not only the reactor, the pumps, the electric power supply, the piping, all need to be very high quality. And that is where quality is again and again and again referred here. Okay, now we come out of the reactor, and what does this fuel, the 200 MeV equivalent. Normal term in which we state, since it does not have a calorific value, it will depend on how the reactor has been designed and what nature of fuel you have used, enriched fuel or natural fuel, and how you are conserving those neutrons, whether you have put excessive material inside which will absorb extra neutrons. So it will tell you how much energy you can deliver from one reactor per ton of fuel, either megawatt days per ton, or these days SI units, we call it gigawatt days per ton. And what it represents is cumulative fission energy produced related to mass of the fuel. 1 ton of fuel I put, enriched or natural uranium, it delivered this much of energy. And then we had to take it out because of the physics limitations in the reactor. The reactor has not been designed to be operated beyond that, and mostly it is plus minus number. For example, in PHWRs, the average burn up is around 7,000 megawatt days per ton or 7 gigawatt days per ton. And where we use enriched fuel like 5% or 4.8% or 3.8%, we may touch 50,000 megawatt days or 50 gigawatt days per ton. Plus minus, some reactors will give 45, some will give 55. So this is the energy. Now with this energy, if you look at the PHWR fuel bundle, which is 13.4 kilograms of uranium, half a meter long, about 3 inches in diameter. I'm sorry, I was trained in inches, so the mix-up. So this small bundle is equivalent to 270 tons of coal, good quality coal, not Indian coal, which is 40% ash. So 270 tons of good quality coal. So that is the energy of 13.4 kilograms of natural uranium is giving. And therefore, in PHWRs, every day we have to open the reactor. You open the reactor, load 8 new fuel bundles. So 270 into 8. So we are saving every day this much of coal in a 220 megawatt PHWR. 700 will save much more. And therefore, this much of carbon dioxide somewhere else is not getting produced. So that is the advantage of nuclear. You use very small amount of fuel and you save a lot of carbon dioxide, and therefore it is called green. Now, so we have discussed radioactivity. We discussed about the fission products which are created after this uranium atom breaks. We discussed about the energy, but what happens to those 3 neutrons which are created? What happens to those? We need only one to sustain the reaction, to sustain the chain reaction. Normally you would have heard that the reactor has gone critical. Critical means you started with 1 neutron or say 10 to the power 14 neutrons per centimeter square. Again, at the end you are having only 10 to the power 14, not more than that. If you have more than that, then you are in a dangerous situation. If you have less than that, reactor will stop. So what do you do to those spare neutrons which are there? Two spare neutrons were produced. What do you do to them? And that is the design physics people do and engineering both put together. These neutrons which are created, one of them anyway is needed to break the next uranium atom and the next uranium atom. So we must see that you are able to sustain this reaction and still have spare neutrons. These spare neutrons are at very high energy. The water which we put in the reactor actually slows down. It is like a billiard ball. Hydrogen neutron is equivalent to a proton, and hydrogen atom has got only one proton. So like billiard ball, they interact with each other and slow down. Heavy water, which is having double the mass of ordinary hydrogen, it takes many more strikes to slow down the neutrons, and therefore you need more heavy water. Anyway, so some neutrons will escape from the boundary. They will leak out because they are at such high speed, and you have to design your reactor that this leakage is also arrested. So there are simple systems so that these neutrons are pushed back. We call it reflector. But this radioactive capture is very important, and therefore you have to see that this is minimized. You don't use materials in the reactor which use this, and therefore we use zirconium. And we attempt by physics design that they are actually absorbed in fertile material. Uranium-238 is anyway part and parcel of the fuel pellet, so they are absorbed in the fertile material after some slowdown, not fully slowed down. In the intermediate phase, they get absorbed. So the design has to take care that they get absorbed. And if they get absorbed, you create plutonium. But some of them may get absorbed in your pressure vessel. It is made of steel. And if they get absorbed there, they will create unnatural elements, and that will be radioactive. So your pressure vessel is also radioactive now. Anything which you put in the reactor and has seen neutrons will become radioactive. And we intentionally put something like cobalt we put inside because industry needs cobalt-60, and take it out and sell. So you make materials which capture this and give you gammas, or you capture in uranium-238 that spare neutron, and you have to design it very carefully. And these are called fertile materials. As I said earlier, if uranium-238 absorbs a neutron, it produces plutonium-239, and you cannot avoid it. You have to design it that in the intermediate energy, that neutron gets absorbed somewhere and produce plutonium. And this is the issue of, so a nuclear reactor in general produces power, and it also converts fertile material to fuel. If you had put thorium somewhere in the reactor, it will also get converted. It will also get it. So it produces power as well as converts fertile material to fuel. So it produces fuel. Therefore, more reactors and more power to follow, and therefore sustain nuclear energy for years to come. That uranium-238, which to start with we said is not a fuel at all, can be gradually converted. Yes, conversion will be very small because the initial ignition point is only 0.7%. So somewhere less than 0.7% you will get, but you get and you reuse it. Plutonium is a better fuel in some circumstances compared to uranium. It will give more neutrons than uranium gives, and therefore you can produce more plutonium. The chain can go on. So a nuclear reactor produces power as well as fuel. And this is what happens. We used uranium, which was natural uranium. Again, I'm talking example of PHWR to simplify. And at the end, you have a lot of unused material. Uranium, anyway, we could not use fully 0.7%. We used 0.5%, and 0.2% is left on an average. 98.8% of uranium-238 also remains unused. And plutonium, which got formed, immediately started participating in the reactions and started giving us heat. But at the end, we still had some plutonium in the pellet. In the pellet inside, this is there, and radioactive waste, 0.7%. Because we used only 0.7% plutonium and uranium put together to produce power. So this is the only waste. So waste is only negligible. A small fraction of this is also very long-lived. Very small fraction is long-lived minor actinides, which is not produced by fission, but the neutron absorption process. So we have, this is very important, we have lot of unused material. Unused also has this, which is a fuel. And we have very small waste. A nuclear reactor creates very small quantity of waste. It uses small amount of fuel, it creates very small amount of waste. And this is important for us. And that is where safeguards come. Dr. Grover yesterday explained in detail. The people who have, those 5 countries, they don't want others to have. What is NPT? NPT is that I can have, you cannot have. So they don't want us to have plutonium, or they don't want world to have plutonium. They don't want world to enrich fuel. Because as Dr. Grover yesterday explained, you need just 5 kilograms of uranium, plutonium, pure plutonium-239, or 15 kilograms of pure uranium-235, and you can make a weapon. And that is the concern, and therefore safeguards. So uranium which you import right from landing in India, it will be monitored by IAEA at all steps. If you are manufacturing fuel, each and every gram of that is counted by IAEA. They will put cameras and they will physically visit. And when you use in the reactor, how many fuel bundles you have put on, how much you have taken out, how long it was in the reactor, what could be the calculated value of plutonium, and they have their measurement techniques to find out also. So this is safeguards about, and you have to be, all the private industry has to be very careful on this. A single error, and yesterday Dr. Grover explained, it will be a question on Government of India, not on that industry. Now, after the fuel is discharged, it has to be cooled again, and therefore it is kept under water, spent fuel storage bay. The fuel bay, just like a swimming pool, you keep it under water, and above the fuel, a certain amount of water has to be always present, provide shielding. Water provides shielding. So around 2 to 3 meters high water layer has to be there at all given times. And all these operations were very critical, but it has to be stored now for a long, long time. This is where the world is stuck today. Most of the countries are stuck at this level. After a certain amount of years, maybe around depends on how much was the burn up and what type of fuel you use, 5 to 10 years, you can take out this fuel into air, and air cooling is sufficient. Cooling in air is sufficient. That is where the fuel transport is allowed by regulators. You can now put it in some concrete cask, maybe one bundle, few bundles in a cask, and it can be cooled by normal atmospheric air. That much heat it can remove. And therefore, the whole world is keeping fuel like this. When I say whole world, it includes US to start with. They are keeping the spent fuel like this, stored like this in concrete casks, and a huge amount of fuel is being stored. Yesterday, I think Dr. Manchanda also mentioned this. And eventually, their plan, which is declared plan, is that this will be permanent storage, will be deep geological storage. When there is a large amount of cooling has already happened, which is around 40 years or more, where there are some fission products like cesium, which gives high heat that cools down. You can store it in a copper clad flask underground in a mine-like structure. Just like uranium mine, this is there. I have been to a Finland assembly which should start operation this year, they are planning, to store such fuel. So it is stored permanently. It has very long life. And we are saying that it will be monitored. I do not know how can you monitor for so many years. So India has not accepted this principle right from the day one. And it is made very clear, yesterday again, it was mentioned, I think again by Dr. Grover, that Shanti Bill in preamble says we will recycle the fuel. We will recycle the fuel. It is said in the preamble of Shanti Bill. So after storage of spent fuel, the fuel has to be given back to Government of India. Only today they have not spelled out how long you have to store. Now they call it, in the textbooks they call it nuclear fuel cycle. But is it a cycle? It is open. It is not a cycle at all. But it is in the textbooks, and when trainings are given, they say it is a nuclear fuel cycle. It is not. It is an open cycle. So how much fuel, I have very rough calculations, though this fuel will be enriched. I am ignoring that enrichment part. And for the present 400 gigawatts or 390 gigawatts, somebody yesterday, we are using this much of uranium, either by enrichment or natural form. And in all this uranium, the fuel is only this much, 470 tons. That is 0.7%. We enrich that, that is a separate issue. But fuel is only this much. So from this much fuel, we are running today 390 gigawatts in the whole world. And what happens? This is the only waste which it has after it is done. Only 440 tons the world has to dispose of. And in return, you will also get a lot of plutonium and lot of unused uranium, that is 99% and more, almost 98.8% unutilized. So this is unutilized. The way it is being stored today in those concrete casts or underground. So this is all unutilized, and you are storing all this fuel, treating this whole thing as a waste, whereas the waste was only this much. Therefore, reprocess, which is a chemical process. Fission products are all chemically different than uranium. So, chemically they can be taken out from uranium. Uranium behavior and chemically will be different. Plutonium is different than uranium chemically. So, you can separate out plutonium chemically. So, you separate them out. And so, these are all the fission products. This is plutonium and large amount of unused uranium. You are taking them out. So you have separated out that 440 tons of the world. If you can separate out, the waste is only this much, very small. By reprocessing, all the above can be separated, and unused uranium and plutonium can be further used in fast breeder reactors. Plutonium is a very good fuel for in the fast flux. The neutrons are not slowed down. It produces more neutrons than uranium-235, and therefore it can produce more plutonium than it consumes, and it's called breeding. It can breed fuel, and therefore uranium-238, which you could not use, can be put to use and regularly converted into plutonium, make more and more reactors, and no mining to be done. No mining to be done now any further. Mining operations can be stopped till you have consumed the last uranium-238. So that is the advantage of reprocessing. And in India, yesterday it was told that the first reactor, Tarapur 1 and 2, which is American reactor, was commissioned in 1969. But you see that reprocessing in India began in 1964, before this. So Dr. Bhabha had drawn a plan that yes, we will reprocess. We cannot store all this fuel in this country. And the moment a research reactor was ready, he also made a reprocessing plant. It was inaugurated by Lal Bahadur Shastri, at that time the Prime Minister, I think 1965 or 66, something. 65. So just see the Indian policy. It has not come today in Shanti Bill. It was existing before we landed into nuclear power, that we will reprocess. We will not store all this spent fuel and make this plutonium available for advanced reactors. And that is where he said stage 2, fast breeder reactors, which we are very close now. We have operated a fast breeder test reactor for 40 years, more than 40 years now. Very successfully, and this is the only reactor in the world which has operated so long, a fast breeder reactor. All the world has given up, not essentially because of technical problems, because of political issues, that plutonium, why people should use plutonium. And today, from the waste which is getting created in the reactors, we are separating out some, these are few examples, there are a couple of more, separating out more from the fission product waste. We are also taking out these chemicals, and they are required for the medical use. Cesium, for example, blood irradiation. When somebody gives blood, see that it is disinfected fully, it is irradiated, and BRC is supplying these machines, or Brit is supplying these machines. Similarly, all this is used for cancer treatment. We have also developed technology and using it in one plant for separating out that long-lived waste also. That minor actinides also we are separating out, and we are the only country in the world which are doing it in a practical plant. There is a lot of research have been done. People know the processes, but those chemicals are not available. They have been developed in India. And we are doing this already. So long-lived waste we are separating out. Unused uranium and plutonium we are using and using in the reactors. We are using for last 40 years in fast breeder test reactor, and now fully the PABR is loaded with this. What remains is vitrified. Vitrified means embed the remaining waste in a glass matrix. Glass, because it will not leach. Even if it gets flooded, it will not leach. So we are the country which in the real sense has closed the fuel cycle. The fuel cycle is closed. From the reactor, whatever spent fuel you will store will be reprocessed. Plutonium will be reused in other type of reactors. These minor actinides, which are long-lived, which today we are starting to separate out, will also be mixed with plutonium and burnt out. This also will not remain. So when we have more and more fast reactors or some other type of reactors which we are working on, ADS and all that, these will be also finished. And certain radioactive isotopes we are already supplying for medical use. So what is left with this small amount of waste? Small amount of waste, which is radioactive. But how long? It is radioactive for about 300 years. And amount of radioactivity goes on decreasing quite sharply. So therefore, principally, in India, we'll have to store spent fuel for 300 years. The question has been asked, the cases have gone up right up to Supreme Court, and we have given affidavits that in India, we may not need a deep geological, some facility. We may need, but very, very small quantity, because when we are claiming that all this is chemically separated, no chemical process is 100% efficient. There will be some negligible waste, which will have to be still stored, but how much? So we are not even able today to calculate that when we had need a geological repository. So today it is all being stored very safely within the DAE, and that is where this is not opened up for privatization. This is a very complex technology, and it will be severely under safeguards, and that is still being worked out, because today whatever we are storing is from Indian fuel. So adopting closed fuel cycle, as in India, very few countries have adopted this. The other country which prominently has adopted is France, Russia. China is attempting to do this. Japan is also attempting for a long time. They may come sometime on this, but they have taken a long time. But we are the only country which started doing it before we got into nuclear power. And our waste management, where we are separating out of minor actinides, I think is the best in the world. So this is the curve. This blue line is our waste, which will have 300 years. And we will get rid of such long-lived waste in India. And we'll have waste to store for 300 years. And our calculations show that, okay, interestingly, thorium will not produce this type of waste. Thorium will not produce this type of waste. And our third stage, which people say calculation that 500 years long. So within that 500 years, this will be over. The uranium waste, which you created by fission products, will be over. So there will be something created by thorium. So within that lifespan, it will be over. So at the end of three-stage program, we may not have much waste left in the country. So closing the fuel cycle is necessary for sustaining nuclear power. The Shanti Bill says it starts with S is for sustaining, and that sustaining is possible only if you do closing the fuel cycle, and we are doing it since ages. Now the world is thinking in this direction. US is changing its policy. Their all concern is political, that if this technology is available in every country, they will have plutonium. But plutonium produced in the reactor cannot make a bomb. You need very pure plutonium. Of course, once you have a reactor, you have fuel. You also you understand the physics. You can create that plutonium, but it is under IAEA monitoring. So, and today the whole Iran-US conflict is on enrichment. You can create. So once you have the facilities, you can create it. So that is the concern. But closing fuel is necessary for sustaining nuclear power. That is about fuel cycle. So any questions?
Hello. Thank you, sir, for such a nice talk. We have some limited time. He had given a very nice talk, so The time available for question will be little less, so we'll ask maybe 2-3 questions now, and then during lunch hours we can further continue. So
the questions can be in the in the
that also
evening session.
But anyone has any important question, one or two we can take.
Sir, I have one question, sir. I have written it. In today's day, sir, people are talking a lot about the using the thorium in the existing 700 megawatt reactor or 220 megawatt reactor. Is it feasible? Feasible is the one thing. Another thing, is it economical, or the existing uranium we are using for the breeding the?
Well, this is a very involved question, but I will give my answers to this. See, this fusion, we studied in the training school. Just like you can split a uranium atom, if you can merge two light atoms, deuterium, you will get a lot of energy. Till today it has not happened, right? Same is thorium. Thorium has its own complexities, and we, a lot of papers are being published and people are making, now the YouTube is full of this. But we in this country know thorium which nobody else knows. We have designed thorium, we have done the physics, we have manufactured fuel bundles, we have loaded in the reactors, number of them, around 250 bundles we have irradiated. We have taken them out, we have checked the physics calculations on the irradiated bundles, we checked whether that burn-up was reached, whether that much uranium-233 is produced. We have reprocessed that bundles, and we also know the limitations of their use, why it cannot be used today, including in PHWRs. So thorium cannot be used in existing PHWRs at all, in the form in which they are projecting, mixing with uranium. If you mix with the uranium, it cannot be reprocessed. Then people should offer first reprocessing technology of that fuel and then offer the fuel. That is one. So it cannot be reprocessed. So in fact, they are saying open cycle, open cycle. Open cycle is not policy of India. Secondly, PHWRs are designed for low burn-up. There are a number of physics reasons. I can give a separate lecture on this. They are designed for low burn-up because from one end to the other, you have to create a burn-up profile. That profile takes years. Today we are, 700 megawatt is not reaching 700, everybody is crying. It takes 3 years to create that profile. If you use high burn-up, it will take 10 years. And another 10 years, you have to shut down to change the coolant tubes. You will waste all the fuel, a very costly fuel. So thorium, please don't talk of thorium at all. Department is on the right track how to use thorium. Okay, so therefore I did not touch thorium. It's a very touchy subject.
Thank you, sir.